Hello everyone. In today's video, we discuss a very interesting question, and this question from the metric space part and asked in the GATE 2023. Okay. What is given in the question? C01 is a space of continuous function space. It contains all the continuous functions which maps from the 0 1 closed interval to the real number set R, and this space is endowed with or associated with this supremum metric. It is defined in this way: supremum of modulus of f of x minus g of x such that x belongs to 0 1. Then we take the supreme value. Okay, so the supreme norm is defined in this way, and fn are sequence of polynomials of the form fn x is equal to x to the power n. We know that every polynomial function is a continuous function, so this fn belongs to this C01 space where x belongs to 0 1 closed interval. Then this set P contains all these fn's, and in this question we have to check whether P is totally bounded, P is bounded, P is closed, or P is open in this continuous function space which is associated with this d infinity norm, means supremum norm. We know that the continuous function, when the continuous function is associated with the supremum continuous function space when associated with the supremum norm d infinity, it is a complete metric space. Complete metric space. Okay, because this concept will be used. Complete metric space means in this space every Cauchy sequence is convergent. Okay, I hope that you all know these basic concepts. Okay, so first we will check that this set P is a very interesting set, and this space C01 is an infinite dimensional space. First we will check that P is a closed set or not. First I will show that it is a closed set. Second I will show that it is a bounded set. But interesting thing is that it is closed and bounded, but it has no convergent subsequence. Means in this question the main beauty is that this is a interesting set which is closed and bounded, but it has no convergent subsequence because this space C01 is a infinite dimensional space, and this concept is true. This concept means if a set is closed and bounded, then it is a compact, then it will be compact. But this concept is true for the only finite dimensional space, but our space C01 is an infinite dimensional space. So the Bolzano-Weierstrass theorem cannot be true. Bolzano-Weierstrass theorem says that if a set is closed and bounded, then it will have a convergent subsequence. Mean one type of it is a compact set, but this Bolzano-Weierstrass theorem is true only for the finite dimensional case, but it is an infinite dimensional space. So closed and boundedness is not sufficient to show that it is a compact set. Means every sequence should have a convergent subsequence. This concept is not true. We will see it, okay, in shortly. So let us move to prove that P is a closed set. First we will prove this one. Okay, what is given P? This set P is given this one, and these fn's are defined in this way. First we will show that P is a closed set. Means closed set means what? We will show that P closure is equal to P, but we know that P closure is equal to P union P dash, and P dash is the set of all limit points of P. Okay, therefore it implies that we have to show that P dash is equal to phi. We have to show what? P dash is equal. If we can show P dash equal to phi, then P closure will be equal with P. Means P has no limit point. We will prove this. Okay, P has no limit point means what? Means this set P has no convergent subsequence, because if x belongs to P dash, then there exists a sequence fn which converges to f uniformly, but we will show that this set P has no convergent subsequence. Then we are done. Okay, so to show this thing, first we will check that this sequence fn converges to f which is a discontinuous function, because this sequence fn converges to a pointwise. This is a pointwise convergent, pointwise limit, pointwise Pointwise limit. Pointwise limit means if we put any x which belongs to the 0 close interval and 1 open interval, the limit function will be equal to 0, and if we put x is equal to 1, it gives 1. So our limit function is a discontinuous function. Okay, then we will use a very standard theorem, uniform limit theorem. The uniform limit says that if gn are continuous functions and if gn converges to g with respect to this supremum norm, then g is also a continuous function. Okay, now we will use this concept to show that our set p has no convergent subsequence. Suppose on the contrary, suppose p has a convergent subsequence. Suppose it has a convergent subsequence. Let say it fnk. Fnk is a convergent subsequence of p. Then it should converges to some function f, some function f or some function h. Let us give a different name, some function h. But we know that from the uniform limit theorem, h is a continuous function. This h is a continuous, since our fn are continuous, and this is converging with respect to the supreme norm. This h is continuous, and we know that the uniform convergence imply pointwise convergence, but we know that our pointwise limit is this one. So our h also should be this one. H is equal to f, because the limit function should be unique. Okay, our space is a Hausdorff space, or these are the mappings to the all real number set, and real number set is a Hausdorff space. Okay, pointwise limit should also be unique by using this Hausdorff concept of R. Okay, this implies that h should equal with f, but f is discontinuous. H is discontinuous, but we know that from the uniform limit theorem our h should be continuous. So this is a contradiction. Therefore this set p does not have any convergent subsequence. If this set p does not have any convergent subsequence, then p dash is equal to phi. P dash has no limit point. Therefore p is equal with p closure. Okay, finally we proved that p dash is equal to phi, but we know that the definition of the closure, p closure equal to p union p dash, but p dash is equal to phi, so it is equal with the p. This implies that p is a closed set. Finally we proved that p is a closed set, and interesting thing is that p has no convergent subsequence, and this concept will be used also later to show that p is not a totally bounded set. Okay, next we will proceed to show that p is a bounded set. Okay, so to show the boundedness, we will take two different points. Okay, any two different points fn and fm, and m comma n belongs to the natural number set. Okay, then we will calculate the distance between fn and fm, and these elements are belonging to the set p. So the supremum norm is defined in this way. Supremum metric or supremum metric is defined in this way, and by using the triangle inequality, this number is dominated by this. Okay, and because the maximum value of this thing is 1 and the maximum value of this thing will be equal with 1, so this number is also can be also estimated by this, so it gives equal to 2. So the distance between the fn and fm is less than equal to 2 for all n and m. So we take any two arbitrary points, but their distance is coming less than equal to 2. So therefore p is a bounded set. Okay, with respect to the supremum metric. Now finally we show that p is a closed set and p is a bounded set. Next I will show that it is not totally bounded, but before going to show that it is not totally bounded, first of all we have to know that what is the meaning of the totally bounded set. We know that bounded set means if we take any element, then their distance can be bounded by a fixed constant. There exists a fixed constant, the distance between two elements is bounded by this. Here the fixed constant is 2, and this is the concept of boundedness. but now I am using a different word. It is called the totally bounded set. So totally bounded set means a metric space MD is totally bounded if and only if for every given epsilon, for every epsilon greater than 0, there exists a finite number n epsilon. For every epsilon, there exists a finite number n epsilon which depends on the epsilon, such that this space M can be covered by finite number of open balls with radius epsilon, and these centers belongs to this space M. Okay, means if you give me any epsilon in the geometry sense, suppose this is the space M, this is our space M, then if I am giving any epsilon, so suppose I have epsilon is equal to 1, then this totally boundedness concept is saying that then I can cover this set by finite number of balls with radius 1. These balls have radius 1, then I can cover by using finite number of balls. This is called the concept of totally boundedness, because this space I covered by how many number of balls? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 number of balls means with radius 1. So this is the concept of totally boundedness. Means if a space is given, then I can cover, if and a number is given epsilon is equal to epsilon, then I can cover with a finite number of balls. I can cover the space by using finite number of balls, and the centers of these balls lie in this metric space M. This is the concept of totally boundedness. Now I will use a very interesting result. It says that if a metric space is complete, if a metric space XD is complete and A is a subset of this metric space, and if A is totally bounded, then the A closure is compact. This is a very nice result. I will use this result because our space C01 associated with D infinity, it is a complete metric space, and P is a subset of this. P is a subset of this complete metric space. Now I will show that this space set P is not totally bounded. Suppose on the contrary, P is totally bounded, and P is totally bounded, and P is subset of this complete metric space. So by using the result 1, that P closure is a compact set. P closure will be a compact set. But we know that P is a closed set. This implies that P is a compact set. P closure equal to P. We know that P closure is compact. This implies P is compact because P closure is equal to with P. Means P is a closed set. If P is a compact set, what is the meaning of compact set? If we take any sequence, then it should have a convergent subsequence. But in the particular case, our P itself is a sequence. Okay. Therefore, this sequence Fn should have a convergent subsequence. But in the previous result, when we proved that P is a closed set, we know that this Fn sequence set has no convergent subsequence. Means if it has a convergent subsequence, then there should be a subsequence Fnk which converges to F. Then F will be a limit point of P. But we know that the limit point of P means P dash is equal to phi. But here if it would have a convergent subsequence, then it should have some limit function F. But we know that there is no limit function of P. So this is a contradiction to the fact that P dash is equal to phi. Okay. So hence our set P cannot be a totally bounded set. Okay. So we proved that P cannot be a totally bounded set. Means in this discussion we proved that P is not a totally bounded set, but it is a bounded and closed. And I am telling that this question has a very interesting meaning. It is saying that it is a bounded and closed, but it has no convergent subsequence. Okay. Means it is not compact. So it is saying that along with boundedness it is not sufficient to prove this space is compact, along with boundedness, we should have totally boundedness. Means bounded, if a set is closed and totally bounded, then it is compact. Then it is compact means then its closure will be compact. Means one type of Bolzano-Weierstrass theorem will be true if it is closed and totally bounded, and this is the result 1. Means if a subset of a and the main point is that space should be complete. If a complete space is given, and if you take a subset and that subset is closed and totally bounded, then it should have a Bolzano-Weierstrass property. Means every bounded sequence should have some convergent subsequence which you can expect at that time, but in the infinite dimensional space you cannot expect that closed and bounded imply it should have a convergent subsequence. It is not true. Closed and totally boundedness, and the condition is that it should have a subset of a from complete metric space, then it should have a convergent subsequence. Means Bolzano-Weierstrass theorem is true when the space should be complete and it requires closed along with the totally boundedness. Then you can expect that every bounded sequence has a convergent subsequence. Okay, so let us, I hope that you all understood this concept. Let us move to our last option. We have to prove that P is, we have to check that P is open or not with respect to the D infinity norm. Now I will claim that P is not open. How? Suppose we will prove in the same contradiction argument. Suppose P is open set. P is open means what? Every element in P is an interior point. Okay. So take any arbitrary point Fm belongs to P, and we know that we are assuming that P is open set. So Fn should be an interior point. Interior point means what? There exists a radius r greater than 0 such that the ball BFM r means center FM radius r is completely lie inside P. This is the meaning of the interior point. We can find a ball with center FM and radius r greater than 0 which completely lie inside the set P. Okay. Now I will define a function Hm. Hm is equal with the Fm plus r by 2, and here r is the same, this r greater than 0. Clearly this Hm function is continuous because r by 2 is constant and Fm is continuous because Fm belongs to P and Fms are of the form x to the power m. Okay. So Hm is a continuous function, but Hm does not lie in P because all the elements in P are of the form x to the power m, but it is x to the power m plus r by 2. Therefore Hm does not lie inside P. Okay. So clearly Hm belongs to C01 and this one Hm does not lie P. Now I will calculate the distance between Fm and Hm. The distance between Fm and Hm is nothing but r by 2 because Fm will cancel, then it gives r by 2, and r by 2 is strictly less than r because r is a positive real number. This implies that Hm element lie inside this ball, but we know that Hm does not belongs to P. But in our previous equation 1 is saying that this ball is entirely lying inside P, but we can find an element which does not lie in P. So this is a contradiction to the equation 1. Equation 1 is saying that this ball entirely lie in P, but we can find an element Hm which lie belongs to this ball, but it does not lie inside P. So therefore it is a contradiction to 1. This contradiction is coming due to our assumption that P is a open set. Therefore it implies that P is not open set. Okay. So option D is also false. Means P option B and C are true. I hope that you all understood it very well. Thank you all. See you next time again.